Welcome to this lecture. I am Thibault Renaux for the Belgium group Georucid, and I will present you a design method for profile assembled on support. This work was based on test and on consideration of a bibliographic state-of-the-art. All this work was the subject of the GRISPR project for which Georucid group took part. This lecture is divided in three main parts. First, a contextual reminder concerning core-form steel profiles and more precisely the problematic situations faced by engineers and installers in charge of the design and implementation of flat roof. I will then present you the test campaign carried out during the GRISPR project, the determination of the characteristics accordingly as well as the conclusions as to the observed behaviors. Finally, the detail of the calculation method will be exposed for each type of studied assembly. Georucid Group is one of the main European independent manufacturers of cold-form steel profiles. The technical assistance it provides to its customers and to engineers is increasingly based on calculation method provided by the Eurocode. To do this, it's important to understand the application of such product and the potential problems to be solved. Applications of cold-form steel profiles are varied. These products can be used for several types of floor. In the case of floor with concrete, the deck can be used as formwork or reinforcement participating to the resistance thanks to specific geometric characteristics. We also find the cold-form profiles for the realization of dry floor for which the lightness is the main asset. Purlins and spacers are one of the family of products. They are generally used to support simple skin roofing and cladding or for the local support of external skin. To continue on cladding applications, we also have liner trays for the inner skin of cladding systems as well as sinusoidal or trapezoidal profiles for single skin or for the outer skin. Finally, we have two different types of application for roofing depending on the slope. Trapezoidal and sinusoidal profiles can be used to realize a single or double skin system for pitched roof. For flat roof, these are trapezoidal profiles whose geometry directly influence on performance. Any kind of building are done with flat roof. Commercial area like car dealer or establishment open to public like cinema, industries or collective residential building are examples of application of flat roof made with steel profiles. In order to ensure the compatibility of a steel deck with the destination of the flat roof, it should be checked that the selected product can resist to the loads applied to this roof. Applying the Eurocode, the engineers then determine the loads according to their nature, snow or wind for example, and ways to combine them, while ensuring the possible application of national requirements. The Eurocode 3-13 allows to determine the resistance of a steel deck and thus its choice. This resistance corresponds to a single steel sheet, and considering the classical resistance of materials, the better configuration is to have a steel sheet on two or more spans. But in reality, not all configurations are not optimistic about the resistance. It is not uncommon for the initial design to change due to conceptual changes or compliance with untreated regulations at the beginning of the project. The first example is the implementation of natural lighting, creating a local elevation of loading by wind and snow effects combination. In this case, the steel sheet initially designed to resist to a uniform distributed load in green now has to resist in a second span to a more elevating loading in red. This configuration has consequences since the strength of the steel sheet alone is probably no longer enough, and it's then for engineers to find a solution that avoids increasing the thickness and therefore change the initial choice. The second example is adding or moving smoke extractors. the steel sheet is replaced locally on a span, creating an isostatic configuration. Its resistance is thus reduced, and it happens that it's not sufficient. In this case too, it is for engineers to find a solution that avoids changing the initial choice of the product. In front of such situations, the Eurocodes don't provide reinforcement of steel sheet by assembling. In some countries, national standards give leads. The aim of a part of the GLUISPR project is therefore to propose assembly solutions after experimentally determining their behavior and establishing analytical design procedures. The first step of the project has been to make a state-of-the-art of national standard, finding that the most relevant was the German DIN 18807-3. This type of joint is now included in the harmonized standard 1090-4. It consists to create a continuity on a support with a moment-resisting connection, the ultimate limit state of the whole structure remaining unaltered. This type of joint presents two configurations, a cantilevered end of profile underneath or on top. Recommendations are provided both for the implementation of connection fasteners and for checking the strength of the assembly by calculating a connection parameter K depending of A, the overlap length. GLUISPR project also took into account the feedback from metal frame engineer and installer by study a double overlap joint like in this picture. It consists to have an overlap equitably distributed on both sides of the support. Main objective of such solution is to increase the resistance compared to a single continuous profile. The last solution studied during GLUISPR project, thanks to engineer and installer feedback, is a continuous profile receiving a local reinforcement. The reinforcement length is equitably distributed both sides of the support, and the main objective remains the same than the previously joined solution. During GLUISPR project, the experimental step consists first to perform a campaign of 71 tests in order to validate some information from state-of-the-art and to have a complete database to interpret. The objective of the test campaign consisted to analyze behaviors and results with a continuous profile as a reference case. 4 configurations of assembled profiles were characterized: the 2 variants of the DIN joint, the double overlap joint, and the continuous profile with the local reinforcement. 2 steel decks, manufactured by Gerecid, were selected due to the representing range of web angle. The 2 steel decks were in 2 thicknesses, 0.75 and 1 mm. To study the load-bearing behavior at intermediate support of assemblies, that is to say, to determine the design resistance moment on support and the support resistance, 3-point bending tests were carried out according to Eurocode 3-13. This test consists to simulate an intermediate support, applying a line load presenting a reeds corresponding to the reeds of this support. In such configurations, the test specimen is in opposite position, and a device constituted of steel plates simulates the transversal continuity of profiles. The parameters of the test campaign are the type of assembly, DIN, double overlap, and continuous profile with reinforcement joints, the 2 steel thicknesses, the 2 profiles, the width of the support, and the span length. For each test, tensile specimens complete the campaign. Applying the requirements of Annex A of Eurocode 3-13, the result of each test, in fact the observed resistance, is adjusted with a factor μr depending on the real thickness and the real yield stress of the steel. The statistical setting is performed according to a family of tests as defined at paragraph A63 of Eurocode 3-13 in order to determine the characteristic values of each configuration of assembly. The 2 characteristic values are the intermediate support reaction and the bending moment at support. They are calculated using the presented equations with FUK, the characteristic test load, BV, the width of the test specimen, LV, the length of the test specimen, L, the span length, and G, the self-weight of test specimen. The typical graphic interpretation of the test consists to draw a diagram interaction between the moment and the reaction in function of the span length L. At the end of each test, the failure mode was noted. For the continuous profiles, the failure mode presents a local impression and buckling at the support occurs due to the maximum bending moment. For the DIN joints, when the overlap length is sufficiently long, the failure mode is the same than those of a continuous profile. For the variant of the DIN joint, with a cantilevered head of profile on top, and when the overlap is too short, a slope difference of the overlapping parts was created by a local web crushing at the end of overlap. For the double overlap joint and the continuous profile with local reinforcement joint, and when the overlap joint is sufficiently long, the failure mode is the same than the continuous profile. Before presenting the design method, the main conclusions of the test campaign are the following. For the DIN joint, this type of joint provides the same behavior than a continuous profile with a sufficiently long overlap. This overlap length must avoid a web crippling phenomenon at the end of the cantilevered part. This overlap length should be checked with the verification of the shear force. For the double overlap joint and the continuous profile with local reinforcement joint, conclusions are the same. Both joints provide 2 times 90% of the resistance of a single continuous profile. To be clear, the resistance of the joint corresponds to 180% of that of a single profile. Like for DIN joint, the overlap length must avoid a web crippling phenomenon at the end of the cantilevered part. This overlap length should be checked with the verification of the shear force. For the verification of the shear force for all studied assemblies, this slide presents you the relation to be used in function of the joint. We arrive now to the presentation of the design method for the 3 types of joints. This method can be applied for single overlap joint with cantilevered part underneath or on top. Double overlap joints and continuous profile with local reinforcement are also concerned. It's important to note that loading must be uniform distributed loads. For all studied joints, the implementation of connection fasteners must follow the requirements given by this picture. The design of a single overlap joint with cantilevered head of profile on top must follow 3 steps. The first step consists to verify the resistance of the assembly in the support axis using the design bending resistance and the design support reaction of a single continuous profile. For both loadings, 3 points are considered. Under downward loading, the bending resistance must be greater than the applied moment, the support resistance must be greater than the support reaction, and the interaction between bending and reaction must be checked using the following relation. Under uplift loading, the bending resistance must be greater than the applied moment, the shear resistance must be greater than the shear load, and the interaction between bending and shear must be checked using the following relation. The step 2 is the verification of the web crippling performed uniquely for downward loading. For this verification, the support resistance of the opposite profile position for the maximum support width, usually 160 mm, is considered. This verification consists to assume that the applied effort doesn't exceed half of the considered resistance. The third step is the verification of the connection only for downward loading and determining the parameter K. The verification consists to calculate the maximum value of K for each web and to check if this value doesn't exceed the total shear resistance of the screws. To do that, apply moment on support and shear force are necessary. For the cantilevered head of profile underneath, the design is a little shorter. Like previously, the first step consists to verify the resistance of the assembly in the support axis using the design bending resistance and the design support reaction of a single continuous profile. For both loadings, 3 points are considered. Under downward loading, the bending resistance must be greater than the applied moment. The support resistance must be greater than the support reaction, and the interaction between bending and reaction must be checked using the following relation. Under uplift loading, the bending resistance must be greater than the applied moment, the shear resistance must be greater than the shear load, and the interaction between bending and shear must be checked using the following relation. For this configuration of single overlap join, no need to verify the web crippling. We arrive directly to the verification of the connection under downward loading using the same protocol that previously, but considering only the applied moment to evaluate the maximum value of connection parameter K. The design method for a double overlap join is divided in 5 steps. For the first step, we had to determine the bending moment distribution under downward loading and for uplift loading, in particular the moment values at the ends of overlap, M1 and M2. Step 2 is the verification of the profiles at the support axis with 90% of the resistance of overlapping products. Under downward loading, each point of verification considers the total resistance for moment, support resistance, and combination between moment and reaction. For uplift loading, the same consideration is applied for moment, shear, and combination between moment and shear. Knowing moment distribution from step 1, it's possible to perform the step 3 consisting to verify the resistance of the assembly at the ends of the overlap. The applied load at the end must be first calculated using this relation. Under downward loading, this load is acting as a tension force on the web, and the verification is subdivided in 5 points. Checking the bending resistance at the 2 ends of overlap, checking the shear resistance, checking the interaction between moment and shear at the 2 ends. For uplift loading, the applied load acts like a compression force on the web, and the verification is subdivided in following 5 points. Checking the bending resistance at the 2 ends of overlap, checking the reaction resistance, checking the interaction between moment and reaction at the 2 ends. It's important to note that for this step 3, resistance values of the profile in the opposite position must be used for both cases of loading. Verification of web crippling is a step 4. It is not relevant for uplift loading, but necessary under downward loading. As for single overlap join, the support resistance of the opposite profile position for the maximum support width, usually 160 mm, must be considered in order to verify that the applied effort doesn't exceed half of the considered resistance. The final step 5 is the verification of the connection parameter K, knowing the applied moment for one web and for both cases of loading. The maximum value must be lower than the shear resistance of the screws. For the continuous profile with local reinforcement, the design method is similar to the double overlap join. In the first step, we had to determine the bending moment distribution under downward loading and for uplift loading, in particular the moment values at the ends of overlap, M1 and M2. The step 2 consists to verify the profiles at support axes with 90% of the resistance of overlapping products. Under downward loading, Each point of the verification considers the total resistance for moment, support resistance, and combination between moment and reaction. For uplift loading, the same consideration is applied for moment, shear, and combination between moment and shear. Knowing moment distribution for step 1, it's possible to perform the step 3, consisting to verify the resistance of the assembly at the ends of the overlap. The applied load at the end must be first calculated using this relation. Under downward loading, this load is acting as a tension force on the webs, and the verification is subdivided in 5 points. Checking the bending resistance at the two ends of overlap, checking the shear resistance, checking the interaction between moment and shear at the two ends. For uplift loading, the applied load acts like a compression force on the webs, and the verification is subdivided in following 5 points. Checking the bending resistance at the two ends of overlap, checking the reaction resistance, checking the interaction between moment and reaction at the two ends. It's important to note that for this step 3, resistance values of the profile in the opposite position must be used for both cases of loading. Step 4 is the verification of web crippling. It is not relevant for uplift loading, but necessary under downward loading. As for single overlap join, the support resistance of the opposite profile position for the maximum support width, usually 160 mm, must be considered in order to verify that the applied effort doesn't exceed half of the considered resistance. The final step 5 is the verification of the connection parameter K, knowing the applied moment for one web and for both cases of loading. The maximum value must be lower than the shear resistance of the screws. I am Thibault Renaux for Jean-Lucid Group, who participate to the GRISP project. This lecture was for the design method of assembled profile. Thank you and enjoy Eurocode.